So as always, once we have gone through sort of the concept of equilibrium, I want to go over some examples of the problems that you're going to work and run into. These again are in chapter 14 of your textbook. This is example 14.2. It's on page 630. If you happen to want to look at that and look at their examples, I don't necessarily follow along exactly what they do, but kind of solve it my own way. So sometimes you might find some benefit in looking at their solutions as well. So here's your question. We've got an equilibrium process. We know that because we've got this double arrow. It's a reversible reaction. And it's been studied at 230 degrees Celsius, which doesn't really matter as long as we're looking at that temperature. So we are. And it says in one experiment, the concentrations of the reacting species at equilibrium are found to be, and it just details those for you, a concentration for each part of this reaction, reactants and products. So that's a little different than the kinetics that we were doing before. Calculate the equilibrium constant, which is Kc, at this temperature. So the first thing that I need to do is write my equilibrium expression. So K equals products raised to the power of that coefficient. So the concentration of NO2 to the second power over reactants raised to their coefficients. So NO, nitrogen monoxide, I should say, to the second power times the concentration of oxygen. And it's just to the first power, so that's understood. So there's nothing really difficult about this. It's just plugging into that equation and solving for K. So concentration of nitrogen monoxide is there. Let's just rewrite here. So 0.0542, it's molarities squared. The oxygen is at 0.127. It's molarity to the first power. And the nitrogen dioxide is at 15.5. And that one is also molarity, and it's also squared. So then it's just a matter of plugging into your calculator. 15.5 squared divided by 0.0542 squared times 0.127. And you get an equilibrium constant of that. I've got 3 sig figs in all those numbers, so 6.44. I'm going to do scientific notation, of course, times 10 to the 5th power. And that's it. If you remember, this does have a unit with it. Molarity squared over molarity to the third would be molarity to the -1. We don't include those units with an equilibrium constant. So that's good news for a lot of you. All right, we'll move on to another problem just to show you a couple of possibilities here. This is example 14.3. It's on page 631 in your textbook if you want to look at that one. So here's your question. The equilibrium constant Kp, so this is in terms of pressure, for the decomposition of phosphorus pentachloride to phosphorus trichloride and molecular chlorine is found to be 1.05 at 250 degrees Celsius. So now they're giving me the constant. And here is the equation. If the equilibrium partial pressures of the phosphorus pentachloride and the phosphorus trichloride are given here, respectively, that means this one goes with the first one, this one goes with the second one. What is the equilibrium partial pressure of the chlorine at this temperature? So again, first step is always write your equilibrium expression. So for this one, K is equal to pressure of PCl3 to the first power times the pressure of Cl2 to the first power, because their coefficients are all 1, over PCl5. Sorry, pressure of PCl5. Again, to the first power. So I just need to plug in what I know and solve for the chlorine concentration, which I don't know. So again, there's my equilibrium constant. So 1.05 is equal to the pressure of the PCl3, which is the second one here, times the pressure of the Cl2, which is what I'm looking for, divided by the pressure of this phosphorus pentachloride, which is this one, 0.875. These are in atmospheres. Just be sure your units match. Usually they don't mess with you on units on these types of problems. So I'm going to multiply both sides by 0.875. And then I'm going to divide by 0.463, just doing the math there. And I get 1.98. So the pressure of the Cl2 is 1.98. And since everything else was in atmospheres, that's all in atmospheres as well. So again, nothing too difficult or too taxing about that, I hope. Just a little bit of math. Now the next thing we're going to look at is that conversion that we talked about from a Kp to a Kc. So this was in your PowerPoint. This is your equation for that. If I've got a pressure, an equilibrium constant in terms of pressure, I can convert it to the one in terms of concentration. And they're related by this RT factor because, again, PV equals nRT. And if you simplify that down, the pressure is related to the number of moles per volume of that expression, because molarity is the number of moles in a liter in the volume of gas. So that's why this works. So here's your reaction. Nitrogen gas plus hydrogen gas, 3 moles of hydrogen, give you 2 moles of ammonia. And the Kp is 4.3 times 10 to the negative 4 at 375 degrees Celsius. And I just want the Kc for the reaction. And so there's my formula for this. So I'm solving for Kc. I'm going to plug in what I know. Kp is 4.3 times 10 to the negative 4th. That's equal to Kc, which again is what I'm looking for, times RT to the delta N. So R is your universal gas constant. We typically use the one for atmospheres. So that's 0.0821 times the temperature. So they're giving you the temperature there in Celsius. As you know, we always have to use Kelvin. So that's 648 Kelvin. If you didn't see what I did there, just add 273 to that to get your Kelvin temperature. And then to the delta N power. And so delta N is the difference in the number of moles of gases between your products and your reactants. And the sign of this matters. And it is products minus reactants. So I've got 2 moles of gas in my products. I've got 1 plus 3, which is 4 moles of gas in my reactants. So delta N here is -2. Then it's just a matter of simplifying your equation. So I'm going to do this part first. 0.0821 times 648. I'm going to raise that to the -2 power. So I get Kc times 3.53 times 10 to the -4th equal to 4.3 times 10 to the -4th. And so if I divide both sides by that, I get 1.22. And so simple as that. Again, it's just a little bit of math that you have to be careful not to get too bogged down in, but it's not a difficult calculation. One last one. And this is just going the other direction. If you're given a Kc, finding the Kp. So methanol is manufactured industrially, gives you the reaction here. We do end up with gaseous methanol at 220 degrees Celsius. So what's the value of Kp? It's a little bit easier because you don't have to rearrange for this one. So Kp is equal to Kc, 10.5, times RT, so R is 0.0821. The temperature there, 220 plus 273 is 493, I think. And then I have to get my delta N. So there's 1 mole of gas in the products. There are 3 moles, oops, can't hear myself. 3 moles of gases in the reactants. My answer is -2 for my delta N there. So 0.0821 times 493, raise that to the -2 power, and then times 10.5. So your Kp is 6.41 times 10 to the -3. And that's that. So guys, I hope that was helpful as you start to work through some of these problems on your own. I'll be talking to you soon, and good luck with your work.